Okay, I decided to try something a little bit different for some of these future lectures. After sitting through a 1 hour long or so presentation on using Zoom for teaching, they suggested it might be a good idea to use the video. I am not a big fan of having myself videoed. I feel very awkward doing it, but if in some way, in just the messed up times we're in right now, if in some way somebody finds it a little bit comforting to see my face at the beginning and during the lecture, it's worth doing it. So what I'm going to do now is I am going to record the last bit of the clay information. This is looking at the structure of phyllosilicate clays particularly. I am going to go ahead and share my screen right here. And so let me just go back a little bit. I finished up last time talking about humus. And of course, humus is an organic form of a sort of clay-like substance. Well, now I'm going to spend time talking about layered clays, which in particular are the phyllosilicate clays. And these have a regular structure to them. They have a definite crystallography, which means that they can be studied and can be classified in various ways. And that may be one of the reasons, as I said, for why these clays tend to be more heavily studied than the others. Also, a lot of them are economically important. A lot of these are the clays that are used, for example, in drilling mud. A lot of these are the clays that are used for pottery and for other types of processes like that. There are a number of industrial processes that use clays. And so these tend to be the phyllosilicate clays, and so that's probably why they're heavily studied. Phyllosilicate clays essentially are composed of two different sheets. There's a silicon-based sheet, and then there's a second sheet that is either magnesium or aluminum-based. So these different types of sheets are what compose the clay. And the number and the arrangement of the sheets give the clay their specific structure. There are 1-to-1 clays, and then there are several types of 2-to-1 clays. And I'll talk about these a little bit more a little bit later on. So silica tetrahedral sheets are the first type of layer that you see in a clay. It is a silicon atom surrounded by 4 oxygen atoms in a tetrahedral arrangement. I'll show you a picture in a moment. These are arranged in a tetrahedral shape, and when you look at it in drawn out as the layers, it essentially looks like 2 layers of oxygen with a layer of silicon between them, and sort of a silica or a silicon sandwich, it's sometimes described as. And the different silicon atoms share oxygens. So it makes a big sheet that just spreads out over area. Now, I mentioned isomorphous substitution in one of the earlier lectures. This is where you have an atom, a different element of different charge but similar size, replacing the primary element in the sheet. Well, here it's not at all uncommon for the silicon, which is a 4 quadrivalent or 4+, to be replaced by aluminum, which is trivalent or 3+. So what you wind up with, you have 4 oxygens, each with a negative charge. In the standard setup, you have silicon 4+, 4 oxygens, each with a negative charge. You wind up with neutrality. But if you put an aluminum in there, then you get 1 leftover negative charge. And that's how cation exchange capacity begins to develop in these clays. So here is the setup with the silicon and the oxygens. You can see this was my attempt at drawing it very simply in PowerPoint. Here are the silicon atoms. Here are the oxygens. Now these back here, these that I have shown as larger would be like sticking forward out of the screen. This one would be sort of pointing back to give you sort of a 3-dimensional appearance. A better depiction of this is like a bird's eye view. This was grabbed from University of Bristol's Mineralogy Department lecture on clays. And you can see each of these little pyramid shapes that are arranged in a hexagon are going to be a silicon surrounded by 4 oxygens. And this is from University of Georgia. This is an attempt to show it in a couple of different ways. This is a ball and stick model right here in the center. This is looking at it from the side. So this would be like you had a piece of the clay. If you could see in scanning electron microscope scale, you would be looking at it from the side view on. And so what you would see then would be, here is one silica and oxygen sheet. Here's another. This is a space filling version of it, which might be a little bit more realistic depiction of what it would be like if we could actually see on a subatomic level. And then this is just a simplified version with polyhedra, where again, you've got kind of like the pyramid shapes there. This is again the bird's eye view. Here you can see this is kind of like what I shared earlier from the location in from the site in Britain. Here is looking down on it. Here, that little blue dot right there is your silicon. So here's one tetrahedron. Here's another tetrahedron. You can't really see the silicon. Or here's another tetrahedron. Here's another one. Some of them, it's a little bit hard to see the silicons in them. Here's the space filling model. So that's the silicon tetrahedral sheet. The second one you get is an octahedral sheet. And this is either called alumina or magnesia, because you have aluminum or you have magnesium in them. Most commonly, they're called an alumina sheet. And so it contains aluminum or magnesium, and there are going to be 6 oxygen atoms per 2 aluminum or 3 magnesium. So again, you see the charges would kind of balance out. The oxygens link together to form an octahedral shape. And depending on whether you're talking about aluminum, that would be dioctahedral because there are 2 aluminums there, or trioctahedral, that would be for magnesium. And again, and I'm just turning my pages here, again, you can kind of visualize these. This is from University of Bristol. This is showing the trioctahedral layer and the dioctahedral layer. Again, this would be dioctahedral with aluminum, trioctahedral with magnesium. And here is the University of Georgia version. Here they're showing the ball and stick model. So here would be your either aluminum or magnesium. Here are your oxygens. Again, the oxygens are shown in red. Here is looking down on it from above. Here is the polyhedra. What they're showing here is the dioctahedral version with aluminum. So that little green dot there is supposed to be your aluminum. And then this is the bird's eye view. This is looking at it from the side. And again, you can have isomorphous, sometimes called isomorphic substitution in there. The isomorphous means literally same shape. Iso is same, morph is shape. So these are going to be about the same size, but not necessarily the same charge. So in the silica sheet, which you saw earlier, this is common when aluminum replaces a silicon at one or more of the sites. And this is going to lead to a net negative charge because you have the leftover negative charge. And so that's where your cation exchange capacity is going to come from, at least the form of it that comes from isomorphous substitution. And so you get that electronegative quality. Well, you can also have this in the octahedral sheet as well as in the tetrahedral sheet. And so what this does over the entire clay particle is it develops a negative charge that will vary from clay to clay and will affect its ability to attract cations. Remember, the cations will be adsorbed with a D to the surface. Now, I do have the YouTube captions on. YouTube doesn't always recognize all of the words, but it is adsorbed with a D, not absorbed like what paper towels do. So you can also have isomorphous substitution in your octahedral sheets where you have aluminum. So in the tetrahedral sheets, sorry, aluminum replaces silicon. Iron can also replace silicon. But then in your octahedral sheets, you can have a number of different replacements as well. in all of these cases, you're pretty much going to get a net negative charge. So isomorphous substitution tends to lead to negative charge. Now, the ions can be, they need to be the same size, but again, the charge can be different. And then you have your silicon sheet, you have your magnesia or alumina sheet. You can arrange those in different ways. The first way of arranging them is a one-to-one arrangement, where you have a tetrahedral sheet and an octahedral sheet that are stuck to each other. So this is symbolizing the tetrahedral sheet. This is symbolizing the octahedral sheet. There is a strong attraction between them, so they stick together. And you get what's called a one-to-one clay. And here, if you can see this, the tetrahedral sheet is shown in white. The octahedral sheet is shown in red. They strongly bond to one another and they don't separate. There's no way anything can get between the layers, okay? They're going to be held strongly in that arrangement. That's a little bit different from what are called 2-to-1 clays. So in your 1-to-1 clay, you have one type of setup. In your 2-to-1 clays, you have another type of setup. And they're classified as 1-to-1 versus 2-to-1, depending on the arrangement of the sheets. So you've already seen 1-to-1 clays where you have a tetrahedral sheet and an octahedral sheet. They will tightly bind to one another, and I've tried to represent that with these pieces of sticky foam to show your layering. And multiple layers are going to be held together, again, by hydrogen bonds. Hydrogen bonds are important here, just as they're important for interactions with water. These bonds are relatively stable in this case, so these sheets don't separate. You can't get anything going in between them, which is different from the 2-to-1 setup. These are clays that are not shrink swell clays. They stay pretty stable when they're wet versus when they're dry. They're also not real plastic like the shrink swell clays can be. So you don't have water or nutrients entering between the layers. So the good side of this is you don't have that shrinking and swelling, which can be a big problem. And I know a lot of people who have lived in this part of the country for a long time, you know shrink swell clays are bad for home foundations. But the downside of it is they have a lower ability to hold nutrients than the shrink swell clays do. So looking at these in a little bit more detail, again, I said these are non-expansion. They have a lower nutrient availability than your 2-to-1 clays do. And the best known one of these is kaolinite. Kaolinite is, when it's very pure, it's a whitish colored clay. And as I said, this was very valuable for pottery making. In fact, we call a lot of that type of fine pottery China because the original forms of it came from that country. So the original good quality, high quality porcelain was made in China. Now, eventually the rest of the world learned the secret of doing that. And some locations, there were some in the UK, for example, that found they had deposits of this type of clay. And so potteries grew up around it. And the very fine china was often very, very thin. The famous thing, the Balik potteries, which were in Ireland, they could make teacups that were so thin that you could hold them up to a light and you could see light through the bottom of the teacup, but they would still hold liquids after they were fired and glazed. And in fact, my parents, somewhere down through the family, it came down to them that they got a few old Balik teacups, and by golly, you can do that. You can hold them up to a light and you can see light shining through the bottom. But they're strong enough to hold hot tea and to hold liquids. Now, obviously, if you drop one, it's not so great, but it's it can be made into very, very fine, thin layers. Kaolinite is also stable. So building the foundation of your house on a kaolinite clay, not going to be a problem. This is a depiction of a kaolinite clay. Here's the tetrahedral layer. Here's the octahedral layer. Now here's the next set. And they're going to be bonded to each other in this space so that you don't get expansion. This is the chemical formula for kaolinite: aluminum, silicon, oxygen, and hydroxide. Now this is in contrast to the 2-to-1 clays. And I want to find, I have my box here with my different arrangements. Okay, here is my fine-grained mica. Here are the things that represent water. Here is one of my 2-to-1 layers. And I should have another one in here somewhere. Okay, there's that. So you have these 2-to-1 clays. It's 2 tetrahedral sheets surrounding an octahedral sheet. So this would be one layer: tetrahedral layer, octahedral layer, another tetrahedral layer. So this is a 2-to-1, and they'll stack up. But the problem is those 2 tetrahedral layers that are in contact with one another, they don't tend to bond together strongly like the 1-to-1 clays do. Because with the 1-to-1 clays, you have tetrahedral, octahedral, tetrahedral, octahedral. Here, you've got tetrahedral, octahedral, tetrahedral, tetrahedral, octahedral, tetrahedral. And so what's going to happen then is, in some cases, stuff can get in between those layers. These are your smectite clays. Smectite are your shrink swell clays. You also have vermiculite clays. This is different from the kind of clay, vermiculite material you buy at the garden center. That's something that's commercially produced. It's different from a true clay. And then you have fine-grained mica, which is another type of clay. And you have chlorite clays. The one I'm going to focus on here is smectite. What smectite will do, you've got these different clay domains, these different layers. When it gets wet, which I'm going to represent water by these pieces of blue foam, water can get between the layers. And as you get more and more water going between the layers, those layers are going to expand. And it doesn't look like a lot here because I can't get all my layers of blue stuff in easily. But when you've got a lot of water in there, that clay is going to expand quite a lot. Well, then when it dries out, it's going to shrink back down. And that's where you've got the problem with shrink and swell. So you have shrink swell clays. This is because the individual tetrahedral, octahedral, tetrahedral sandwich is only very weakly bonded to the one next to it. And so stuff can get in between. So water will enter between the layers and it'll force them apart. And the clay will expand when it's wet and shrink when it's dry. And this is what causes foundation damage. This is why there are so many foundation repair companies in our area. I mentioned when I moved down here from Illinois, which tends not to have shrink swell clays, I was totally unfamiliar with things like ramjack. But they're all over the place here because that's a genuine problem. However, the upside of smectites is they have higher nutrient availability because in addition to water fitting between these layers, more nutrients can fit between them. There's a bigger surface area for cation exchange capacity. The most common form of smectite is known as montmorillonite, named after Montmorillon in France. A lot of these clays, a lot of these things are named for the location where they were first described from. So this is showing montmorillonite. Here you've got the tetrahedral, octahedral, tetrahedral. This is the layer where cations and water can penetrate. And then here's your next layer. Then you have vermiculite clays. As I said, this is different from the vermiculite you buy at Lowe's or at the nursery store. These are 2-to-1 clays that have a trioctahedral sheet. So they specifically have a magnesium-based sheet in them. They have a lot of isomorphous substitution. So again, They are going to have a lot of nutrient holding capacity, but they don't tend to swell as much as smectite clay. So they're a little bit better from that standpoint, at least from a foundation perspective, because you don't get those big deep cracks forming in the soil. And they do have a high cation exchange capacity in them. Now you can have some other things going on as well. You can have fine-grained mica, which is also known as illite. My model of fine-grained mica here, I have little pony beads stuck in between there. Those represent potassium ions, because potassium ions get in there in this particular clay and they form a bridge between the different layers, and they stop those layers from shrinking and swelling. So it stabilizes them. And these tend to form big particles of clay, relatively speaking. All clay is very small, but this tends to form relatively large particles. This is the result, as you might guess from the name, when mica-based minerals weather. And again, this has some degree of isomorphous substitution, so it does have cation exchange capacity, maybe not as much as a smectite clay would, but it's less expansive than a smectite clay. And then finally, you have got a chlorite clay, which has a hydroxide layer, which I have shown here in green, between the layers. Again, that forms a bridging layer. And so that hydroxide sheet bridges the layers and prevents the clay from being a shrink swell clay. These tend to be high in iron and magnesium. And then also here is a map of the US showing generally, now this is not entirely accurate, I don't think, because, well, there's a little bit of kaolinite here. We do have a considerable amount of smectite. I think this line is a little too far west. But notice Illinois, very high in illite, not a shrink swell clay. That's why I was unfamiliar with the whole concept of foundation repair companies when I moved down here. Eastern part of the US, kaolinite, there were a lot of potteries in Georgia and in other parts of the Southeast. Up here, there's a mixture. Here, there's a mixture. We have a lot of shrink swell clay right throughout this area of southern Oklahoma and North Texas. And then subtropical areas have these sesquioxides, these highly weathered clays. You can see the very southern tip of Florida, and then also the Hawaiian Islands. They're also probably going to have some of those amorphous clays that come from the volcanic ash as well. So in soil, you can have a big mix of different types of clay. It is not as consistent as you might think from looking at the textbook. There are also intermediate types. Clays are very variable, and we're trying to classify them in a way that makes them seem extremely set, and that's just not the case. So, and also some clays don't have a highly defined crystalline structure. When clays form, as I said, this is through chemical weathering of primary minerals. You get losses and substitutions, which lead to your fine-grained micas, remember, with the potassium ions bridging them. And then you also get just complete breakdown and recrystallization, which is going to happen in some of your other clays as well. The charges on clay colloids, I've already talked about these a little bit. Constant charge comes from isomorphous substitution, which I've already gone into some detail about. Variable charge is when you're looking at the surface of the clay and the functional groups on it. This is especially where humus comes into having charges, because humus has a lot of acid groups, a lot of carboxyl groups on its surface, and these can gain and lose hydrogen ions. When they've lost a hydrogen ion, they have a negative charge. When they gain more than one hydrogen ion, they can develop even a weak positive charge. And so variable charge depends on the pH. It depends on the hydrogen ion, whether they are present or whether they have been pulled off. So variable charge is highly pH dependent. These are OH or COOH groups, so it's going to be hydroxyl groups or carboxyl groups on the surface of the clays. When a hydrogen ion is lost, so you've got an OH, pull that hydrogen ion off, you've got O negative, negatively charged oxygen. And so that negative charge then gives a cation exchange capacity. But this is going to depend a lot at soil pH. As the soil becomes more acid, that variable charge is going to be lost. And so the ability to hold cations is going to be lost in a more acidic soil. At extremely low pH, you may get what's called protonation, which would be an additional hydrogen ion joining on there and giving it a positive charge. I'm going to kind of skip through this quickly in the interest of time. This is isomorphous substitution. I've already talked about this. Constant charge is called constant just because it's always there. This is tied into the structure of the clay. So in soils, nutrient availability is going to be strongly related to cation exchange capacity, which we symbolize as CEC. AEC is for positively charged. It's anion exchange capacity. We can measure this. This is the thing I talked about in the earlier lecture. And we can predict how strongly things will be held, depending on some of the properties of the soil, a little bit beyond the scope of this class. And we also have, as I mentioned, anion exchange capacity. This is considerably rarer, and this is largely because of protonation. This is going to be a variable charge. This is going to be pH dependent. So this would involve negatively charged substances, but this is far, far less common than cation exchange capacity. So this will show the opposite pH pattern for cation exchange capacity in a soil. So that's the end of the slideshow material. I am going to go ahead and stop recording now, and I'm going to see about trying to upload this last little bit, which is going to be the end of chapter 8, which is going to be the end of the material on clay mineralogy.